we'll go ahead and get started. Before I start, any feedback on this past week? The content, the homework, anything? Questions, problems?
For the histogram, I believe about the resistant bacteria. Any rate, it was. Is there a? Are you going to specify like how large each bin, the span of each bin should be? I mean, that's just for practice. I mean, right?
Yeah. So.
Is there a general rule?
No. Okay. So in this class, we are going to learn classical statistics. We're going to learn how to do a lot of tests and a lot of things by hand. Okay. The truth is that today, if you were to do statistics, you will not likely do very many things by hand. Okay. It's like in elementary school, you learned multiplication and long division, but now, if you had to divide a large number, you would most likely just throw it in your calculator and get something out. So that said, I think there is some merit in learning how to make a histogram by hand. There is some value in seeing that changing bin widths can result in a histogram that looks somewhat different. And so is there a rule on how wide a bin needs to be? No, there is no perfect rule, and people have debated the issue, but it's not that big of a deal. Okay, you can throw it at a computer and say, make me a histogram, and it will make one for you, and you can say, well, try it with this bin width, and it will make a new one. And you can say, try it with this bin width, and it'll change it up. And so anyway, does your choice of bin width matter? Yes, but also not really. Okay, so that's, say, depending on the situation, it's okay to have wide bins or small bins. Okay, generally with experience and by looking at many different histograms, you'll get an idea when your bin width is too wide and when your bin width is too narrow. I guess unfortunately in your book, all of the histograms that show up in section 2.2 have pretty nice bin widths. Okay, those would all the bin widths that show up in section 2.2, with the exception, I guess on page 34, they tried to show the effect of having bin widths that are too narrow, or possibly even too wide at the top. In our book, most of the histograms have nice bin widths. When you make bin widths on make histograms on the computer doesn't know any better, and it will just kind of choose an arbitrary bin width, or there might be some kind of formula or algorithm that it uses to determine bin width, and it may not result in the best looking histogram. And you may choose to want more bins or fewer bins depending on your situation. So it might be a worthy exercise to go online and search histograms, bins too wide, bins too narrow, and just see what results. Okay, I think the key from that histogram section is, can you read a histogram and understand what it's saying? And if that's good, good. Other questions? Okay, some of you, I understand maybe this is your first class. Maybe you missed last week's class. So if that is the case, the class website, I've written on this board, so it's not going to show up in the video, but if you are watching the video, you've obviously found the correct website. So the class website is up there, so make sure you have that in your notes. When you click that, you will find the syllabus and also homework and videos from last week's lecture and things of that nature. I hope the organization of the website is to your satisfaction. If you have comments or suggestions, you can send me a message. Some of you have joined the Facebook group. I know it's only been 1 week, and so there's been zero activity in terms of discussion, but that's okay. As you guys face issues or have questions, don't hesitate to post to the group. All right. Then, standard deviation, did that go okay? Watching the video, calculating standard deviation by hand. So may I ask, what is the point of having a standard deviation or calculating the standard deviation? What does the standard deviation tell us?
The measure of spread.
It's a measure of spread, okay, and
Which is the typical distance from the mean.
okay, a typical distance from the mean. So if we have a set of data and it has a large standard deviation, then that would indicate to us that values that are different from the mean is not very surprising. On the other hand, if you have a set of data and the standard deviation is very small, then we expect most of our values to be very close to the mean. And so, just like any of the other measures of spread, the IQR or the range, it gives us an idea of how similar or dissimilar the numbers are from one another. And the standard deviation can be thought of as the typical distance points are from the mean. And it will come into play later on in the course as we take a look at data more in depth. Today we're going to cover probability. Okay, and so probability are the rules of randomness and random chance. By learning probability, we understand how likely or unlikely something is to happen by random chance alone. Okay. A very simple example is we can flip a coin, and we understand that the chance the coin will land on heads is 0.5. Even though we have no idea whether the next coin flip will be heads or tails, when we flip the coin, we understand that the chance that it will land heads on the next coin flip is 0.5. So that's what we will, we're going to cover a bunch of rules of probability, which will form kind of the foundation and basis for inference. Inference looks at data and uses our understanding of probability to tell us how likely our data was or how unlikely our data is to be observed under certain assumptions. So, anyway, let's talk about chapter 3, the rules of probability. In our course, we are taking what we call a classical view or frequentist view of probability. So when I say I flip a coin, and the probability what does it mean to say the probability is 0.5?
50% chance.
Okay, we're just replacing the word probability with chance. So what does it mean that the chance that it lands heads is 0.5?
Half a chance.
I'm sorry?
Half a chance.
Half a chance, okay. All right, so how do we define chance then? Okay, I feel like we're just replacing the word probability with chance. Can somebody define what probability or chance equals 0.5? What does that mean?
The likelihood that a particular outcome is going to be.
Okay, so we have some synonyms: probability, likelihood, chance. We're saying this, whatever. Take your word, probability that the coin lands heads is 0.5. The chance that it lands heads is 0.5. The likelihood that it lands heads is 0.5. But what does that mean?
For every one time?
I'm sorry?
For every one time?
Okay.
In the chapter, it's saying event.
Event? Okay, so the event would be that the coin lands heads. Okay, so maybe I'm reaching for something that you are not equipped to answer yet. Okay, so the idea is, right, if I flip a coin, we have no idea whether it will land heads or tails. But there's some intuitive notion that says the probability or the chance or the likelihood that it lands heads is 0.5. Okay? But what does that mean? Okay? When we take a classical or frequentist view of probability, what this is saying is that if I were to flip the coin many times, like if I flip the coin a million times or a billion times, out of those million coin flips, I expect about half of those coin flips to land heads. Okay? But any one particular coin flip, I have no idea whether it will be heads or tails. Okay, so even though I cannot about the long run frequency, or long run relative frequency, I should say. In that if I flip the coin a million times, I expect the proportion of times that it lands heads to be very close to 0.5. Will it be exactly 0.5? Probably not. If I flip a coin a million times, the only way that the proportion of heads to be 0.5 would be if I got exactly 500,000 heads and 500,000 tails. That's probably not going to happen. But I will have something probably close to 500,000 heads in comparison to a million coin flips. Okay. If I flip the coin twice, I will not necessarily have one heads and one tails. Okay. If I flip the coin 10 times, I will not necessarily have 5 heads and 5 tails, but I could expect something something reasonably close to 0.5, maybe 0.7 heads, or even 0.8 heads is possible, although less likely to happen. But if I flip the coin 1,000,000 times, or 1,000,000,000 times, the overall proportion of heads versus times the coin was flipped should be close to 0.5. Does that jive with our intuition and our understanding? Okay. And so when I say the probability that the coin lands heads is 0.5, that is talking about the long run refers to the long run, and long run being potentially infinite, okay? So even after 1,000,000, that is technically not enough for the long run, it's a lot, but refers to the long run relative frequency. Frequency that the coin lands heads. And so this is how the classical frequentist view of probability defines the definition of probability. There's other viewpoints. In particular, there's the Bayesian view, which talks about a measure of belief, but that's not the approach we're taking. The implications of this are that, well, this understanding, I think, it's easy to understand when we're talking about events that are repeatable, such as a coin flip. Okay, we can imagine, even though it might be practically impossible to actually flip a coin an infinite number of times, it's easy for our brains to imagine flipping a coin many, many, many times. It works well for rolling a die, picking a card out of a deck, all of these types of things. However, it becomes a little bit more difficult when we're talking about things that are not necessarily repeatable. So, you know, if somebody is diagnosed with a disease and they say the probability that you survive longer than 2 years with this disease is 10%, the frequentist view requires a, quote, repetition, a long-run repetition. And obviously, for an individual, it is not possible to have repeating events such as this. But I guess a frequentist view would be, say, imagine, you know, freezing this moment in time and creating infinitely many parallel universes, okay? And then we see how the events unfold. And in 10% of those parallel universes, this person with the disease will survive longer than 2 years. And in 90% of the parallel universes, this person will not. Okay, that would be the forced way of applying this classical frequentist view of probability. Okay, it's the idea that we can repeat something many, many, many times, and if we look at the long-run relative frequency, the overall frequency will be this value, 0.5. Okay. So this brings up the idea between empirical probabilities or empirical frequencies. Yeah, let's see, empirical versus theoretic probabilities. theoretic probability is that for a coin, the probability that the coin lands heads is 0.5. That would be our theoretic probability. The empirical probability would be the probability that we observe based on evidence. Okay, so to get empirical probability, requires us to actually flip a coin many times. Okay, so let's say I flip a coin once. So after one coin flip, let's say the coin lands tails. Okay, so my empirical probability at this point empirical probability of heads so far is I've observed 0 heads after one coin flip. My empirical probability is 0. Is that concept okay? Let's say I flip it again. So after 2 coin flips, and my second coin flip is also tails. What is my empirical probability for heads? 0. So my empirical probability for heads is technically 0 out of 2, also 0. Let's say on my third flip I get heads. What is my empirical probability? So after 3 coin flips, I've observed heads once out of a total of 3 flips. And so my empirical probability is 0.333 thus far. Perhaps I flip the coin so after 20 flips, maybe the number of heads I've seen is I've seen 8 heads and tails 12 times. Okay, so my probability after 20 coin flips is 8 out of 20, which would be what is that, 40%? Something like that. So this is my empirical probability. Maybe after 200 flips, I've seen 105 heads and 95 tails. So my empirical probability would be 0.525 or something like that. So far, so good? This is just hypothetical. This illustrates what we call the law of large numbers. Which states that if I repeat something many, many, many times, the empirical probability of some event is expected to approach, or is expected to be closer to the theoretic probability of that event. So after a few coin flips, if we are keeping track of our relative frequency, it may not necessarily be 0.5 or close to 0.5. It could be, by coincidence and by perhaps luck. We could have empirical probability that's 0.5 or very close to 0.5. But we also can't expect that it will always be close to 0.5 if we've flipped a coin just a few number of times. But after many coin flips, 200 coin flips, or 1,000 coin flips, or so many coin flips, the empirical probability should be, or we can expect the empirical probability to be closer to the theoretic probability after many, many tries. This concept is illustrated with a table and kind of this graph in the book. And basically it's just graphing the empirical probability after so many trials. This idea okay? So we have a few general rules. Okay, a few rules. So maybe we have some event. Some event A. A could be the coin lands heads. A could be I win the lottery. A could be I don't know, just that it rains tomorrow. Okay, some event. So coin lands heads. That it rains tomorrow, or the Washington Nationals advance, or whatever. Okay, whatever it might be, we have some event. Okay, then we would say the probability of that event is written probability of A, or maybe just P of A. These are interchangeable, whether there's an R or not. This is the probability that the event occurs, okay? So it's important that we distinguish between the event A itself and the probability of the event. Because we can define probability of an event with a number. So the probability of an event, of some event A, is always going to be between 0 and 1. The probability is equal to 0, then A will never happen. Never happens. Never, meaning never. And if probability probability of A equals 1, then A always happens. I guess you could say over here A is impossible and A is certain. You want to put things in different words. But most of the time, it would be some number between 0 and 1. Okay. What is the probability that the sun rises tomorrow? Something very, very, very close to 1. Okay. There is an off chance that something terrible happens. Okay. But that's what we have. Okay. So we'll say the probability of A is between 0 and 1. Okay. We have. If there is A, then we also have, if A is the event, if there's an event A, then we also have what we call the complement of that event, meaning the instance when A does not happen. Okay? So if A is the coin lands heads, what would be the complement of A? It is the coin does not land heads. Okay? Generally, that would mean the coin lands tails, but it could also be that the coin was eaten by an eagle while it was in the air or something, okay? So if A is the probability that the coin lands heads, the complement of A would be the coin does not land heads. If A is that it rains tomorrow, the complement of A would be it does not rain, okay? So the complement of some event is the event where A or that thing does not happen. Complement of A means A does not happen. I should say is complement of A is the event, or is when A does not happen. Okay, and we might write the complement of A as not A, or it's also written as A complement or A prime. These are different notations for saying A does not happen. Okay. I find that students prefer this, saying not in front of A. But just keep in mind that these are saying the exact same thing. And the probability of the complement of A, so the probability of A not happening or not A is equal to 1 minus the probability of A. So let's say A is coin lands heads, and we say that the probability of A is equal to 0.5, then the probability of not A is equal to 1 minus 0.5, which equals 0.5. And we might define not A being tails, and say everything else is impossible or negligible. When we have simple outcomes, we can find our theoretic probabilities rather easily. simple outcomes. These are experiments where every outcome is equally likely. So this would be things like flipping a coin, because getting heads is equally likely as getting tails. Or rolling a die. 1, 2, 3, 4, 5, and 6 are all equally likely. At least they should be. Drawing a card drawing a random card from a deck. Each outcome equally likely. So for random experiments with simple outcomes, we can say the probability of some event is equal to the number of simple outcomes in the event divided by total number of simple outcomes. So I think this is all just very simple. Make things more complicated in the moment here. So for example, if I say, are we all familiar with a deck of cards? Anyone is a little shaky? There's 52 cards in a deck, 4 suits, 13 values in each suit. Okay. So if I say, let A be that the chosen card is a face card. So a face card is Jack, Queen, or King. Ace is not a face card. There is no face on an ace. It's a high value card. But if we're talking about face cards, strict face cards, Jack, Queen, and King. What is the probability of drawing a face card from a shuffled deck?
12 out of 52.
12 out of 52. Okay, so the probability of drawing a face card is equal to 12 out of 52, because there are 52 cards total. Face cards. Okay. 3 in each of the 4 suits. What would the probability of not drawing a face card be?
40.
Okay. So the probability of not A would be 1 minus the probability of A. So 1 minus 12 out of 52, which is equal to 40 out of 52. Because if we remember how to do fractions, we turn 1 into this. Alright, well, you should all know your fractions. So we have that. Okay, good. But be careful, because for this to work, have to be dealing with random experiments with simple outcomes, or outcomes that are equally likely. If I ask you, if I say I roll 2 dice, what is the probability that the sum is 9? Do we have, can we calculate this easily? Okay, so what are the outcomes for rolling 2 dice? So, let me tell you the wrong approach. So the wrong approach is to say, okay, the outcomes for the sum of dice are 2, 3, like when you roll 2 dice, you can get as small as 2 for the sum, and as high as 12. The wrong approach would be to say, well, 9 is one of these outcomes, so we have a 1 in 11 chance. Okay? So this is wrong. Okay? Because each of these outcomes are not equally likely. And I hope we can see that. Because it is not, if you've ever played Settlers of Catan or Craps or some other dice-based game where you're rolling 2 dice, you know that it is not likely for the dice to roll 2 as it is to roll 7 or 6 or 8. Okay. So the correct approach would require a listing of all 36 outcomes. And then, so dice 1 has, and dice 2 has this, and then you have to check off which of these add up to 9. So there are 4 ways to create 9 out of a total of 36 possible die rolls. So each of these 36 are equally likely. Okay? So 36 possible dice combinations. Each are equally likely. Four combinations add to 9. So probability that we get a 9 is equal to 4 out of 36. That's what we got. Okay, is that good? Sometimes we have situations where we want to calculate more complicated probabilities. Okay. So I could ask a question such as, let's draw a random card from a deck. And I ask, what is the probability that it is a face card or a heart. Well, anytime you see the word or,